Do you have any preliminary questions or things that you would like to quickly address? Okay, so today we will talk about harmonic oscillators. Okay. Okay. So more precisely, we'll essentially solve the following problem. Suppose that I have in 3 dimensions something like this. So this is the usual p squared divided by 2m, so the Laplacian. And then I have a potential that is 1 over 2m, m omega squared, the distance from the origin squared, okay? Notice, I might slightly generalize this problem. You see, this is totally invariance by rotation, but in fact, I might write something like 1/2 m omega x squared plus omega y squared plus omega z squared. Okay? So in other words, rather than considering a sphere, I consider some kind of ellipsoid. So the 3 axes are in principle different. We might solve this. Now, this problem and the variance come in many circumstances where perhaps the exact potential is not precisely quadratic, but close to a minimum. You can expand it and develop somehow an harmonic approximation, and from that you learn quite a few things. For instance, let's consider the typical problem of molecules, vibrating molecules. Okay, for instance, H2, okay, hydrogen. Okay, the potential energy between the 2 hydrogen atoms as a function of the distance r between the 2 atoms will look something like this. Okay, the typical form is this kind. Okay, so obviously as the 2 atoms go far away, then they go to some value, which I will call the 0. Okay, this is obviously the 2 energies of the 2 separated atoms. Okay, as you go to very close distance, the electrons will feel each other, and there is a Pauli repulsion, the thing, and also the 2 nuclei in the end see each other very much, and therefore this will strongly diverge. But there is an interesting intermediate region where, in fact, the potential shows a minimum. Okay, so this is the typical distance where that the molecule would like to have. Close that region, okay, you have something which is a quadratic potential, okay, which obviously is not perfect. You see, there are deviations from this side and deviation from this side, but nevertheless, if you calculate what is the quadratic approximation and you somehow draw the first levels of this quadratic potential, you get the vibrational frequencies of the molecule pretty nicely. Okay? So it's important in many contexts. For instance, phonons in solid are essentially a glorified version of this problem. Okay, so the vibration of a full solid essentially is built from this exercise. Okay, before I proceed, let me show you some general approach by which sometimes you can reduce a 3-dimensional problem, like here, for instance, to solving 1-dimensional problem. This is called separation of variables. Okay? In this case, it's pretty simple. Okay? You solve directly separate variables in Cartesian coordinates. Sometimes you need a bit more skillful things. For instance, for the hydrogen atom, we will separate variables into radial coordinates, and the separation is slightly more complex. We will study this later on. But this somehow illustrates, in its simplest possible version, the problem. Okay? So, essentially here I have a Hamiltonian for each of the three coordinates. Let me call it I. So I is, say, x, y, and z. What is it? It is the momentum along that coordinate squared divided by 2m plus 1/2 m omega square. Let me just do for simplicity, the case. Okay? So x, this is a notation to mean x square or y square or z square. Hopefully this is clear. Sometimes I will call x a combined thing with an index. Sometimes I will just specify x, y, or z, but hopefully this will bring no confusion. Okay, so suppose I know how to solve this 1D, this is a one-dimensional problem. Can I glue together the solutions of these one-dimensional problems that I have done for the x, the y, and the z to construct a solution for the three-dimensional problem here? The answer is yes, and the approach works as follows. So suppose that I have solved my 1D problem, so I have found eigenfunctions. Let me denote phi I means x, y, or z. They have some index, okay? N, the variable that they depend on, equal to some value of the eigenvalue, okay, times the same function, okay? Hopefully this is clear, although there are a few indices here and there, okay? This is essentially h phi equal to e phi. N is the index of the different eigenfunctions, okay, which we will find. I simply reminds us that in principle the functions might be different for x, y, and z. For instance, if you do this problem, the functions are slightly different for x, y, and z. Okay, so I keep track of that if you want. And in the same way, the eigenvalues might depend on x, y, and z, because, for instance, I have done this, this, or that. Okay? So this is to keep the thing a bit more general. All right. Then, given these solutions, I can form. Let me write it here. Okay. But no, I'll write it here, although it's pretty uncomfortable. So I form a function which will depend on the x, the y, and the z, okay? So the three coordinates made as follows. I take the solution for the x dimensional problem, okay, with the x, okay, with index n, okay, and I keep track of the index here. Then I take the solution of the y problem, okay, with index m, okay, and then I take the solution for the z problem with the index, let's call it L. These are arbitrary labels, okay? So I take three solutions, one for the x, one for the y, one for the z, generally different, obviously, M, L, M, M, L. So I have here a collection of indices and the three variables. Notice I multiply them, okay? Then the somehow theorem, although it's a very simple statement, is that this object here is such that the full Hamiltonian h of phi n m l of x, y, and z is equal to phi n m l x, y, and z with an eigenvalue which I can calculate easily, and is simply En for the x problem plus En for the y problem plus Ez for the Z prop. Okay? So I can call this somehow the eigenvalue associated to the triplet of indices M, L, M. Notice, here there is a product, and here there is a sum. Not a product, obviously, otherwise the dimension is not right. Is it clear? This is the statement of the separation of variable that we see here. The proof is very simple. Essentially, it uses the fact that, remember that X and Px, they do not commute, right? Px is equal to IH bar. But X and say Py, they commute. And so X and Pz, and Y and Px, okay? So different variables belonging to the different somehow directions commute among each other, okay? And that's the crucial thing. So let me just take this function and apply the Hamiltonian. Remember, the Hamiltonian, I have essentially written it as the Hamiltonian for the x variable plus the Hamiltonian for the y variable plus the Hamiltonian for the z variable. You see, the Hamiltonian is sum of three pieces, and these three pieces commute among each other. The x and the y's do not feel each other, and the y and the z also, the x and the z, okay? Internally, I have to be careful to the commutators, obviously. X and Px do not commute, but in between, they commute, okay? So let's try to write exactly what I have here. Here I have hx, I substitute, plus hy plus hz, okay? And I should apply to this function here, which is a product of three functions, okay? So I write for a second in all details, okay? X, phi, y, n, m, c, z, l, okay? Let's try to see. I apply the first piece, okay? Now, the first piece applies directly to the first Hamiltonian, to the first eigenfunction, okay? So the result is the same function, right? So I write it here. Okay, times some number, which I read from here, is En of x. Is it clear? Okay? Good. And this is the first. Now I do the second. I have to apply this to this term here. Now, obviously, here I have x and px, y and py, and they first have to get in touch with this x thing. But they commute. In particular, py and x commute. So you can bring the whole thing right close to this function here. Okay? At that point, the application of hy to phi is simple, because you know this is an eigenfunction of hy. What is the eigenvalue? Well, in general, say n, so let me write it as plus em for the y. Okay? In general, it's a possibly different, well, you read it from here. Good. What about the third? Well, the third, same argument, right? Z goes directly to the z, is an eigenfunction with an eigenvalue El. Okay? So plus El of z. Okay? All of them multiply the same function, because these objects are eigenfunctions. So the object is just like this. Okay? And there is the result. Okay? So it's a very simple, straightforward somehow exercise. Clear? Okay, this happens in other circumstances. For instance, I could give you suppose that I have a square well, but not in one dimension, but in two dimensions. So the potential is 0 except on a square or on a cube. Then you can separate variables in the most trivial way, x, y, and z. Or the potential might be more complicated. For instance, square well in the y and harmonic in the x. Again, you can separate. Okay? There are several possible simple combinations of things that you could do. Here? Okay. Now, having played with the separation of variables, let me now concentrate on a single one-dimensional harmonic oscillator, which is the goal of the next. So here I have a single 1D, so this is, say, let's call it X, okay? I take away the vector nature, okay? Good. Now the goal is to find, again, what I just erased, the eigenfunction of this problem, okay? So in principle, I would like to find functions, again, so H, a function of X, okay, which depends on some index N, and which, such that if I apply the Hamiltonian, I get back some eigenvalue times the same function of X, okay? Now what is this? This object, so written explicitly minus H bar square over 2m, the second derivative with respect to x squared plus 1/2 m omega squared x squared. Okay? So now, before we had only problems with essentially zero potential or constant potential. We did lots of square well types of things. Now the potential is non-zero, but it's quadratic, and therefore we can solve things exactly. Okay? So the goal of the remaining part of this lecture is to learn to solve this problem. Okay. Obviously, you realize it's a differential equation. Okay? And I might tackle this problem as, let's try to find solution to this differential equation. This is an eigen value problem for functions, which somehow leads to a differential equation. Now, this is not particularly useful in this case because there are quicker and more somehow easier to follow methods to establish the result. And I will follow this trick because there is an algebraic solution. The usefulness of it is that we get acquainted with objects like the creation operator and the destruction operator A and A dagger, which are very useful when you do second quantization later on. In particular, the second quantization of bosonic particles is precisely the thing that we will see today. Okay, glorified and with more indices. Okay, so somehow we do two things in one shot. We solve the harmonic oscillator, but we also somehow get acquainted with the formalism that is useful for many indistinguishable bosons. Okay, now before I proceed, however, I want to teach you how to get rid of annoying objects, like for instance the mass, the h bar, omega. I mean, some of them are fundamental constants. H bar is fundamental, so it's not annoying in some sense, but it's, I mean, you don't want to put h bar on your computer, okay? It's a very, very small number. You don't want to write that very small number in the computer. You want to learn how to somehow get results in units of, okay? So what does it mean? It's often written in the papers and so on and so forth. Often you find putting h bar equal to 1, mass equal to 1, okay? Or omega equal to 1. I mean, these in particular are certainly not fundamental constant. Omega, what is the frequency of this harmonic oscillator? Depends on the problem, okay? So it's a very problem given quantity. The mass, well, if it is an electron, is a fundamental constant, but if it is such and such atom oscillating, depends on the... So these are all fundamental or less fundamental constants that are often put to 1. What does it mean? Why? And how, if you solve the exercise, having put everything to 1, and then I ask you, okay, please tell me how many electron volts this energy is. You have to be able to put back all constant, okay, and give me an answer in electron volt, in amps, or in whatever, okay? So the technique is simple, but I encourage you to do it every time you have a problem. Try to spot the dimensionless variables that you might use. Okay? So dimensionless variables. Okay? And be explicit about writing the transformation. Okay? Because this helps, at least when you do it for the first times. Okay? So, the first thing that I would like to show is how to do it here. Okay? So suppose that I have some length, let me call it L. Now, you certainly realize that with this length, if I consider this quantity, that's an energy, right? It's the potential energy associated to a deformation of this spring. This is a spring. A harmonic oscillator is a spring, okay? A deformation of an amount L. On the other hand, if I have a length L, I also have a kinetic energy associated with that, which is h bar squared divided by 2ml squared. We have seen it in the square well problems, okay? We would call it A or something. Now, these are two energies. Let's impose, it's our choice, that the L that I select is such that these two energies are exactly the same, okay? So equal, by my choice, I want it, h bar squared divided by 2ml squared, okay? So you see that the 2 goes. What is L squared? Well, let's first find L to the 4th. L to the 4th is equal to h bar squared divided by the mass square and omega square, which goes down, okay? Which means that, I write it here, L squared is equal to h bar divided by m omega, or if you really want L, that's the square root, okay? Is it clear? This is the solution of this simple algebra, okay? So, given this length, I know that these two objects are exactly the same. Okay, and I can calculate this length. Given what is the mass of the object that I have, what is the frequency of vibration, I can tell you how much it is in meters or in whatever. Okay, good. This is called the oscillator length. Oscillator length. Okay, good. Now, once you have a length, you can measure quantities with respect to that length. For instance, suppose that I ask you, let's measure x in units of that length, which means in practice that I introduce a dimensionless length x. X is more. You see that this is bigger. So it's big X divided by L. Okay? So X tell me how many times L enters into the big X thing. Okay? Is it clear? So this is a dimensionless length. Less length. Okay. Good. What about the momentum, Px? Well, I have the momentum, dimension-full momentum Px big, again, and for what I have to divide to obtain something which has no dimension?
1 over L.
There is also an h bar. right? H bar over L. The momenta have dimension H bar over L, okay? Or if you want L divided by H bar times Px, okay? So this is a dimensionless momentum. Fantastic. Let's start studying what is the commutation rule between X and Px, dimensionless. Okay? Well, X is equal to 1 over L times big X. And Px is equal to L divided by H bar times big X. Notice I put all constant outside of the commutators because you can collect constant outside. Okay? Good. But X and Px, the commutator, is I H bar, right? But L goes away, and notice the H bar also goes away, so the commutator is I. Okay? Multiplying 1. As if H bar was 1. We know where H bar is. H bar is hiding, for instance, in the momentum. Nevertheless, in my nice dimensionless variables X and P, it's as if I can forget about H bar. It's put to 1. Okay. Good. That's the first thing. Now, let's proceed. And let's try to write. So I write it here. To write our Hamiltonian. In terms of these variables. Okay. So H equal to the momentum square, but the momentum is equal to H bar divided by L square times Px squared. The small dimensionless momentum, right? And then it's divided by 2m. Okay, that's the first term. What about the potential energy? Is 1/2 m omega squared. And then I have big X, but big X is equal to L times small x. So this is L squared, small x squared. Very good. Now, you see that here I have this term, and here I have this term. Okay? Or if you want, you can include the factor 1/2. But in particular, you should notice that 1 over m h bar square over L square is exactly equal to m omega square L square by our very definition of L. Remember, we looked for L in such a way that these two terms were exactly the same. So in fact, I can put these two things in common. But let's explore a little bit more what is m omega square L square. Look at this expression. This is equal to m omega square h bar divided by m omega. The mass goes and omega remains to power 1. So it's equal to h bar omega. So what you see here is in fact in this squeeze h bar omega. Okay? So let's continue our object. We put h bar omega, which is this block and this block, as a common factor. Then I put the factor 2, okay, which is in both. And then I have px squared plus x squared. Okay? Or if you want, let's write it like this. Okay? This is our Hamiltonian. It's h bar omega, an energy, and in fact, square. In fact, from the very first lecture, h bar omega, you know, is the energy that Planck would associate to anything of frequency omega. Times an Hamiltonian that now involves dimensionless operators, first of all. It is p squared divided by 2 plus x squared divided by 2. So, look at this object. It's as if n was put to 1 and omega was put to 1. You see? The miracle somehow occurred. But, I mean, it's not a miracle. It's because I purposely wanted to use dimensionless variables in all my construction, okay? But now I have a perfect command of what's going on. So if I want to answer to some question about how much is the energy of this thing, I know that whatever I have calculated, I should multiply by this quantity. So energy somehow are measured in units of h bar omega, okay? That's the natural unit of energy. And if someone gives me some length, but a dimensionless length somehow, I have to multiply by L in order to give back the value in angstrom, okay? So I know perfectly well how to insert again all the constants, whatever they might be. Is it clear? Okay? This is the first thing that you should always do whenever you set up a problem. Even if the problem is not exactly solvable, you simply want to put it on your computer and solve the differential equation or diagonalize your matrix, whatever. Always think the mass, the thing, should I really put these values, ugly and strange values in my code? Most probably the answer is no. Just try to express things in appropriate dimensionless variable, state them at the beginning of the code so that you know what's inside, and try to work out things where most of the quantities are 1. Okay, good. Having done this preamble, pretty long and tedious maybe, but I want to, I mean, it's really useful. Okay. Now I have written my Hamiltonian as h bar omega, some dimensionless Hamiltonian, let me call it h tilde, where h tilde is equal to p squared over 2 plus x squared, okay? So as if everything is 1. Very good.
I have a question.
Yeah.
From the relation that we did here, it
Where?
seems like energy is independent of the mass. It seems like energy is independent of the mass. Why is so?
Energy.
Energy
It is.
seems like independent of the mass. Can we conclude that?
Yes, it is. It depends only on the frequency. It is true. You might be worried and say, hey, why is energy? Well, I'm not saying that the mass doesn't enter. I mean, if I tell you, okay, you have a certain spring constant K, then the associated potential energy is this. Is the energy independent of the mass? Of course not. If you fix K, I know that this K is actually equal to the mass times the frequency squared in my oscillator. So I can equivalently rewrite this in the following way. Which means that the frequency that I calculate depends on the mass. Okay? So the mass is somehow hiding. It depends on what you give me. Okay? If you tell me I have some spring constant of such and such erg per meter or joule per meter, what is the frequency and what is the energy that, well, it depends on the mass, because somehow the mass will force you to calculate a different omega. But once I have omega, then the frequencies, the energies are just h bar omega or multiple, or Well, we will see in a second. Okay? So good question, but the mass is hiding somehow in the omega. Okay. Now, I promised now an algebraic solution. And the solution goes through introducing a strange operator, which is called the destruction operator. We'll see why destruction is a second. As follows. You take x, okay? This is the dimensionless x operator. You add the px. Let me omit the x. There is only one direction, so I'll call it p. Okay. And you just put a square root of 2 there, okay? So x plus ip, x is Hermitian, p is Hermitian, x plus ip is not Hermitian, okay? I do it. If I ask you, calculate please the Hermitian conjugate, I think we have done as an explicit exercise, that's it. It's very simple, it's just minus ip. Okay? Very good. Now, you might be worried and say, but what are those things? I mean, nothing could be actually simpler in terms of operators. Because you know that, for instance, in x representation, this is minus I, no h bar, the derivative with respect to x. Right? So if you multiply times the I, this operator is in fact 1 over square root of x plus the derivative. Okay? That's it. This is x plus the derivative. Is it strange? Well, not particularly strange. It's not Hermitian. Okay, and what is this? Well, it is x minus the derivative. Okay? Okay. So, let's look at their commutator. Okay, so I study now a commutator with a dagger. Okay? Sometimes I will forget about the hat. You know, I mean, these are the operators. Okay? So, let's use this expression. So I have 1 over square root of 2 x plus
1 over 2
ip. And then I have another 1 over square root of 2 x minus ip. Okay? So this is 1 over 2. X with x, nothing. P with P, nothing, so I have to just keep track of this and of that, okay? So x commutator P is equal to I, right? But there is a minus I there, so plus 1. Is it clear? P commutator x is minus I. Remember, the commutators, if you exchange them, so this is minus I times I, another plus 1. Okay, so the result is 1. Okay, so in terms of the operator A and A dagger, the fundamental commutator reads as follows. It is equal to 1. Okay? Good. Now, obviously, I can invert these two expressions and try to determine x and p in terms of A and A dagger. Okay? The inversion is very, very simple, in fact, because these are linear relationships. So, for instance, if you sum these two, okay, what I get? I get that the IP cancels, okay? And this, I get it twice. So, 2 divided by square root of 2, which is square root of 2x, is equal to A plus A dagger. Is it clear? Okay? Which means that I write my first expression here, x is really equal to 1 over square root of 2 a plus A dagger. Good. What other trick I can do to find the p? What do you suggest?
Subtract.
Subtract, of course, right? This minus that. So what I get square root of 2ip from here. And this gives A minus A dagger. Okay? So P is 1 over square root of 2i, A minus A dagger. Okay? Good. we are ready to do our algebra. So we want to write this Hamiltonian now, rather than with the x and p, in terms of a and a dagger. And the answer is, and I will derive that for you, that it is equal to this very simple operator. Okay? So let's prove this. Can I erase? Yes. Okay. Okay. We go by direct substitution. So P is given there. So H tilde is equal to 1/2 the square of that object. So 1 over square root of 2i squared times a minus a dagger squared. Then I have plus another 1/2 the square of that object, so 1 over square root of 2 squared a plus a dagger squared. Okay? Now, careful, these are square of operators. So, although, I mean, you would be tempted to use just a simple square of a binomial, you have to be a little bit more careful because operators do not commute, and therefore the mixed term, you have to keep track of both. Don't sum just simply with the factor 2, as you would do in algebra. But let's go. So this is 1/2. This is I squared is 1 as minus 1, and this is 1/2. So equal to minus 1/2 times 1/2. And then I have a squared plus a dagger squared. And then I have minus a dagger minus a dagger a. Is it clear? I have done the square of the thing, keeping, however, the mixed term separate and in the right order. Clear to everybody? Okay. Then I sum the second thing. So plus 1/2 times 1/2, then square, a square plus a dagger square. And then I have, again, mixed term. This time, however, with a plus. So plus a dagger plus a dagger a. Okay? I put them one below the other because I have to sum them. And you notice that here there is a minus. Okay? So shall we invert the minus and put it here? Minus, minus, plus, plus. Okay? Now there is a plus. Okay? In particular, it's 1/4, 1/4. You see immediately that this and this, they disappear. This and that, they also disappear. And this are the same. Okay? So 2 times this thing. Okay? So it's 1/4 times 2 a dagger plus a dagger a. Is it so far clear? Which is, by the way, 1/2. Okay? Almost the final expression, except that here I have a dagger, but a dagger is related to a dagger a. Remember this expression here, which I can rewrite as a dagger minus a dagger a equal to 1. Okay? Which means that whenever I see a dagger, I can equally well substitute it with a dagger a, but there is a plus 1 that I have to pay. Okay? Good. So here I have 1/2. The first term is a dagger a plus 1, and the second is a dagger a. Okay? So these two give me a factor 2, which means simply a dagger a, and this one, well, is alone, and is plus 1/2, okay? Which is what I wanted to get. Clear so far? Good. So I have taken my dimensionless Hamiltonian, and introducing these two operators, I have rewritten in terms of a dagger a plus 1/2. You might say, so what? It looks like an exercise of introducing things. Okay, well, you will see why this is useful. First thing, suppose that I find the state, okay, such that if I apply A to this state, let me call it phi 0, it's a wave function, okay, an actual wave function, I get 0. Suppose. Can I find it, by the way? Well, I erased, but you remember that A, this object, was 1 over square root of 2 x plus the derivative with respect to x. Okay? So what's written there is simply the following differential equation. Can I solve it?
Yes.
It's simple. The derivative, I write it like this. The derivative, forget about this factor, which is not important. The derivative of phi 0 is equal to minus x phi 0. Any ideas of what might be a solution of this?
One over 2 Gaussian.
You know the solution. Any ideas from those who... When you take a derivative of, you get the same function, this rings a bell, exponential, right? But you don't get quite the same function. If we have just a constant, you say, well, then just let me exponential of lambda x. But here I get x, which means that you have to have an x squared, so that when I do the derivative of the composite function, I get the x down here. Okay? So, good. So this is just to tell you that the solution will be some constant times e to the minus x squared. In fact, let's put the factor 2 there, so that when you take the derivative of this object, you get the minus, the 2 cancels, and you get the x. Okay? C is a constant. Whatever constant would do it, right? Doesn't matter. Okay. So I know how to solve this problem. This is a solution of that problem. Oh, but this technically one says that A annihilates phi 0. Okay? So we'll discuss this later on more. Okay? Now, let's see what happens if I consider the Hamiltonian. So now I have h tilde applied to phi 0. H tilde is A dagger A applied to phi 0 plus 1/2 applied to phi 0. Now, A applied to phi 0, according to what I've written there, is 0. Once you have 0, you can do whatever you want. Is 0. Okay, forever. There is no reanimation that you can do. It's dead. 0. Good. So this goes away. And this is 1/2 phi 0. So I have discovered that in fact phi 0 is not only the function which is annihilated by A, but it's also an eigenfunction of the Hamiltonian. With eigenvalue? 1/2. So this lonely guy here is in fact an eigenvalue of the Hamiltonian. And in fact it's even more than an eigenvalue. It's the ground state. Okay? I want to prove to you that this is the ground state. Okay? So in other words, no possible eigenvalue can be smaller than 1/2. Why? Let's see. Suppose that I have a state, psi, okay? And I want to know, I want to show to you that h applied to psi, scalar product with psi, okay? If this is an eigenfunction of the Hamiltonian, that would be, say, of a certain eigenvalue, this would be E, okay? Say, let's put some, okay? Phi n. This would be En. Is it clear? If this is an eigenfunction, then you take the scalar product, it's Phi n. Now, I want to argue with you that whatever state you take, in fact, let's be more general, whatever psi normalized, psi, h psi should be greater or equal to 1/2. Why? Well, let's look at this expression for h. So this object is equal to psi, A dagger A plus 1/2 psi. Okay? So this first piece is 1/2 times 1, right? Because psi is supposed to be normalized. Then I have plus psi, A dagger A psi. Clear? Okay. Now, let's bring this on this side. What do I have to do? Change A dagger into A, because the dagger of the dagger is A. So this is equal to 1/2 plus 8 psi, 8 psi. Is it clear? The scalar product of the function 8 psi with itself, okay? Which is non-negative. So this is greater or equal to 0. And when is 0? Only if A psi is equal to 0. But 8 psi is equal to 0 is precisely this condition. So psi 0 verifies the lowest possible value of this thing, right? Which is 1/2. Any other state will have a larger value of the energy eigenvalue. Is it clear, the argument? Good. So we discover, in fact, the ground state. There it is, okay? Associated E0 equal to 1/2. Or better, E0 tilde in units of h bar omega. Good. How do I find C? I have to normalize. Okay, so I have to calculate the integral from minus infinity to plus infinity of the modulus square of this thing, so C modulus square e to the minus x square in dx, and I have to impose that this is what? Do you know how to calculate this Gaussian? Yes, we did it in the first lecture, in fact, okay? So you do it, and you calculate what C has to be. Some root of pi, some root of 2, or whatever. I don't even wrote it down here, okay? But you can calculate easily. Okay? Clear so far? So we found our first eigenvalue, eigenvector pair, which is this function here, perfectly normalized, and 1/2. All right, now let me just draw the energy axis here. Okay? So this is the 0. The ground state we discovered, so this is En divided by h bar omega, or if you want the En tilde. Okay? The ground state we discovered is 1/2, not 0. Remember, the minimum of the potential is 0. So in principle, I know that I shouldn't look for any negative energies. But in fact, the lowest state doesn't come to 0. Okay? Remember, for the plane waves, there is a 0 value of the energy, because the plane wave can extend over all space and it can be more and more slowly varying. But here, somehow, the ground state is a competition between potential energy and kinetic energy, and the ground state is, in fact, what realizes the best compromise between the two, which is a Gaussian thing. Okay? So this is my phi0 modulus square. It's a Gaussian wave function, okay, which somehow makes the best it can in minimizing the potential energy and the kinetic energy. Okay? And in fact, I have a simple exercise to solve the same problem by a variational principle. Somehow, suppose that I look for the ground state being a Gaussian. Okay? What would be the object that makes the energy minimal? Well, obviously, this is the minimum. Okay? There is a small exercise that guides you through this variational solution. Okay. Clear so far? Good. Now, I want to show to you that now, from now on, everything is almost straightforward. All other eigenvalues differ by 1, like this. So the next is a 3/2, and then 5/2, and then 7/2, and so on and so forth, okay? So one after the other. And they are created, obtained, by applying a dagger. Do not apply A. A is the killer, okay? So I rewrite it here. Okay, A applied to phi 0 gives you 0, killer. A dagger is called a creation operator, okay? So you can apply a dagger to phi 0, okay? And obtain a new state, which I will call phi 1, okay? Because there is one a dagger that I have applied. And so on and so forth. I can apply 2 a daggers and obtain phi 2, okay? So the next part of the lecture is to show that indeed this simple trick works. Okay. Let's erase a few things. This I can erase. This I can erase. Good. This, let's leave it. Okay? So let's form the state phi 1. Let's get a little practice. Okay? Phi 1 equal to a dagger phi 0. If you want to see it in its face, that's it. So phi 0 is this. A dagger, we know what it is square root of 2x minus the derivative. Phi 0 is the constant times e to the minus x squared divided by 2. Okay? So let's calculate these two objects. So this is equal to c divided by square root of 2. Then I have x, well, x is x, times the same Gaussian. When I take the derivative, well, we calculate it. It's minus, the 2 goes with the 2, minus x, right? But there is a minus now, so it's a plus x. Okay? So before, in the action of the killer, there was a cancellation. Now, there's no cancellation, it's x plus x. So this object is square root of 2c, x times e to the minus x squared over 2. So it's a Gaussian multiplied by just x, a linear function, okay? And we will see that all the states that we obtain are Gaussian multiplied by polynomials. Okay? The simplest one is x. These are polynomials are called Hermite polynomials, by the way. So in this way we are generating Hermite polynomials. Okay, but so far this is just my definition of phi 1. Is this an eigenfunction of the Hamiltonian? The answer is yes. Okay. Let's verify. Okay. So what I do is the following: I take this Hamiltonian, and I apply it to phi 1. Okay. So this is equal to h dagger a plus 1/2 applied to something which is a dagger phi 0. Okay? This is by definition what I need to do. Okay, let's see what comes out. I have a dagger a applied to a dagger phi 0. And then I have plus 1/2 a dagger phi 0. Okay? Good. A is the killer, remember. But luckily, there is a bodyguard. Okay? So A cannot directly act and kill phi 0. First, it has to struggle with the bodyguard. And the struggle is the commutator. Remember, A dagger is equal to A dagger A plus 1 by that. So you mean when the killer goes to the right, it has paid a plus 1. So I rewrite the struggle here in the following way. A dagger A plus 1. The killer has gone to the right. Okay? Plus 1/2 A dagger phi 0. Now the killer acts there and gives me 0. Okay? So this term disappears. This plus 1, however, which is the fee that the killer had to pay, okay, gives me a term that is similar to this. So it's 1 plus 1/2 A dagger phi 0. Okay? Because you see you have A dagger phi 0. But A dagger phi 0 is indeed phi 1. Okay? So here you have that phi 1 is an eigenfunction of the Hamiltonian with eigenvalue 1/2 plus 1. Okay? Which is how many creation operator I have included. Okay? So the statement is now the following. More general. That if you, can I erase here? Yes, maybe I keep track of this. So phi 1 is equal to square root of 2c x e to the minus x squared over 2. And erase. Okay? The more general statement is the following. Define phi tilde n of x equal to the application of a dagger n times to phi 0. Okay? Then the answer is that h tilde applied to phi tilde n of x is equal to e tilde n phi n, where this object is n plus 1/2. Okay? So if I have n of them, here I have n, not 1. Okay? This is the thing that I should deduce, and this is in fact something that I want you to deduce. Okay? So we have done essentially the preliminary gymnastic to understand what goes on. Here you immediately see that what I would need, this is annoying, okay? We have seen it in the face several times. The necessary gymnastic is the following. H tilde, remember, as A dagger, forget about the 1/2. The 1/2 is there, okay, you see? So the 1/2 is a spectator. Fantastic. So the important thing is A dagger A, which is this piece, okay? So the yellow piece. And this acts on A dagger to the power n phi 0. Okay? Now, there is the killer. But there are n bodyguards. Okay? So it has to pay fees to each one of them. One every time it goes behind the bodyguard. Okay? And the net result is an n. Okay? So please show it. I suggest, but you might find other ways, there's a kind of recursion formula that you can prove. But you can also start by proving, for instance, that if the commutator of A and A dagger is 1, but the commutator of A and A dagger to the power n can also be calculated. Remember the rules to calculate the commutator of products. Try to show by recursion that if I have this object here, then that's equal to n times A dagger to the power n minus 1. Okay? Try to show this. Again, perhaps by recursion. because for n equal 1, it's obviously true, right? Suppose it is true for n, and prove that by that assumption you immediately deduce for n equal plus 1, n plus 1 by using the rule of the product of the two commutators, right? A dagger to the n plus 1 is a dagger to the n times a dagger. You use the rule of the product, you assume that it's true for n, and you deduce for n plus 1. Huh? Induction proof. Good. If I have this, then I can use essentially in one step. I can go, the killer can go through the bodyguard, n of them, in one top, because this is telling me that a dagger to the n is equal to n a dagger to the n minus 1 plus a dagger to the n a. Okay? Is it clear? And then if you use this, so here, this is equal to a dagger, where is it? There. N, a dagger to the power n minus 1, plus a dagger a applied to phi 0. But remember, now a, the killer, is close to it, so this gives 0. And this gives me a dagger n times a dagger and a dagger to the n minus 1, a dagger to the power n, phi 0. Okay? And this is precisely phi tilde. Okay, so we proved that a dagger a applied to phi tilde of n is equal to n times phi tilde of n. Okay? This shows two things. First of all, that this object here counts. Okay? It counts. In fact, it's called the number operator. Number operator. Okay? It counts how many times a dagger appears in front of phi 0. It counts the number of bodyguards. Okay? Second, it immediately tells you that the energy is in fact this. Right? Okay? Now, you might ask, why did you write this tilde here? Because, in general, I have to take care of normalization. As written, these states are not normalized, okay? Except for n equal 1 and 0, okay? For n equal 2, 3, and so on, they are not precisely normalized. And the reason is that you can prove, again, with similar techniques. Okay, is it so far clear? You can prove the following thing. Phi n tilde, as written, phi n tilde is not equal to 1, but rather to n factorial. Okay? So for n equals 0 and 1, it's alright, it's 1. But for n equal to 2 on, it's not true. Okay? So the correctly normalized functions, okay, you should put here a factor Cn times the phi n tilde. So Cn times a dagger to the power n applied to phi 0. What is Cn? Well, let's impose that phi n is indeed equal to 1. Okay? But phi n is Cn modulo square times phi n tilde. Did you follow? Okay? But this is n factorial. So it's Cn modulo square times n factorial. What would you take as Cn in order to make the result 1? 1 over square root of n factorial. Okay? So the correctly normalized states are 1 over square root of n factorial, a dagger to the n applied to phi 0. Okay? How do you prove this? Well, if you look at what you need to calculate, you realize what's the trick. What you need to calculate is here I have a dagger n times, and here I have phi 0. On the left, I have the same thing, which means that I can put here phi 0 and put here a to the power n. Okay? So this is exactly what's written there. Is it clear to everybody? This was written before here as a dagger to the power n phi 0, a dagger to the power n phi 0. Okay? Then I move this thing here, making them a. Clear so far? Good. Again, I have the freedom of adding if I want the bar, but doesn't really matter. Okay? Now, it's the problem of n killers and n bodyguards. Now the fight becomes more complex than before. Okay? So, each killer has to go through the n bodyguards, all of them, however. And this brings a factorial. You might say, how do you prove it? Well, let me see the first step of this thing. So, I write this as phi 0, a to the n minus 1, and then I have I isolate the first killer to the right, a dagger to the power n, phi 0. Okay? I use this commutator that you should prove by induction there, and I take this object here, which is written here, and I substitute with that. Okay? Let's try to do it. Let's try to do it. What is it? So I rewrite phi 0, let me write it here. Phi 0, a to the power n minus 1, and then I write this object. So n, a dagger to the power n minus 1, plus a dagger to the power n times a. Okay? Good. I close, and I put the phi 0. No. Yes? Clear? Okay. Now look at this. This is a killer close to the phi 0. So this goes to 0. Okay? So the result of this is the first term only, which is n times phi 0, a to the n minus 1, a dagger to the n minus 1 phi 0. So it's like the previous problem with one less, however, but with the factor n. Now, it takes a very little imagination to imagine an induction proof for this, because this is the same problem as before, n minus 1 step. So this will be equal to n times n minus 1 times the same thing with one step less. So a n minus 2, a dagger to the n minus 2. Okay? And so on and so forth. If you want, you can just, I don't need an induction proof. Just proceed, and it is very clear that as you go and reduce the n here towards 0, you leave out as a factor in front exactly the factorial n minus 1, n minus 2, and so forth. Is it clear? Okay? So this goes all the way to n minus 1, blah blah blah, until you get 1, and then I have phi 0, phi 0. No other no killers and bodyguards remaining. Okay, so there it is, and therefore this is n factorial. And because of this, the correctly normalized states are, I have erased them. Okay, they have 1 over, okay, let's write it here. 1 over square root of n. Okay, good. So, we have accomplished our algebraic solution. You could try for yourself with this phi2, for instance. Remember, we calculate phi1 being the linear function. If you calculate phi2, you will find a polynomial of degree 2, even however. So the x term is missing. So it's some x squared minus 1. I can, presumably I do have it somewhere. No, I don't have it. You do it, okay? Try to do the phi2 and also the phi3, just for the fun of it. Do a little bit of practice. So you have the first 4 states, the ground state, the first, the second, and the third excited states. The ground state is even, first is odd, second excited state is even again, third is odd. Here is the thing. Ground state, forget about the right. This is the function, this is the modulus square of the function, okay? Function, Gaussian. First excited state, x times the Gaussian. You see it has this funny shape, okay? So eventually for large x is obviously Gaussian tail, but close to the origin it's a straight line, okay? This is the second excited state, so it's x squared minus 1 something. Now, far away, Gaussian tails. Close by is a polynomial of degree 2, and therefore there are 2 zeros, right? Symmetrically placed. Polynomial of degree 3, 3 zeros. 1 in the 0, and 2 here and there. Okay? So this is degree 3, and there is x cubed, x, and nothing else. Okay? So really is there is a factor x, and therefore a root in 0 and so on and so forth. Very simple, but just practice a little bit with these things. Obviously, when you take the square, all these negative things just hide up. By the way, this is the thing for degree 20. Okay? So if you look, the modulus square, if you look, there are 20 zeros. And you start seeing something. This becomes, if you insist on going higher and higher, becomes more and more densely oscillating, but on average, if you calculate the average of this thing, it becomes a smooth quantity that in fact looks like this funny 1 over square root thing. If you look at the lecture notes, you will be guided through some classical analogy. Okay, so what is the probability, if I have an harmonic oscillator, a classical harmonic oscillator, what is the probability of finding the oscillator in a given position x? Now, obviously, the probability is larger where the velocity is smaller, right? Because in the origin, the oscillator goes very fast. Close to the turning points, it has to go to 0 in velocity, and therefore you find it more often. And this 1 over square root that you see there is precisely the classical prediction that you would do for an oscillator, a classical oscillator. Okay, so please go and do the analysis to somehow understand that in the limit of a very, very large quantum number, the prediction of classical mechanics, roughly speaking, go hand to hand with the prediction of quantum mechanics. By the way, obviously, when you look at energy scales for which this one is small, for instance, suppose that you have some temperature, and the temperature is much larger than this discrete separation. Imagine that this h bar omega was a very, very, very small energy difference. Okay? Suppose that this was an infrared photon. Okay, it's a very, very small thing. So imagine that this picture here is, yes, discrete, but so much fine that going with a zoom of a certain temperature, which is, say, much larger than that, you wouldn't really notice the discrete nature of the thing. And then, obviously, you would say that the expectation value of my classical mechanics calculation would be perfectly well be obeyed. While when I go with a photon, let's think about photons, where h bar omega is a robust energy. Think of an ultraviolet photon, or even more, X-ray or gamma ray. These are beasts, giant h bar omega. If they catch you, I mean, they can kill you. Okay? Given enough energetic gamma ray, can make a really, disaster in any cell of your body. Okay? So these are big energies. Temperature of 300 Kelvin, 1000 Kelvin, peanuts. Very, very small energies compared to these small things. So at that level, it's not good to disregard the discrete nature of the spacing. Okay? And that's what Planck understood by I don't know how. Okay? He understood that somehow that's the trick. Okay? The correct distribution function is automatically obtained by imposing this discrete nature of the frequencies. And to close the circle, you might ask, you're talking about harmonic oscillator. Why do you talk about harmonic oscillator and you talk about Planck and you talk about photons? Because photons are harmonic oscillator of the electromagnetic field. Okay? You can take electromagnetism and in vacuum and essentially quantize the Maxwell theory in terms of a free set of harmonic oscillator. Okay, obviously with many frequencies. Okay, not just one. And depending on the boundary condition, the problem can become easily reasonably complicated. But in principle, it's a sum of harmonic oscillators like the ones we have described. Okay? So this discrete nature is precisely the same thing we were discussing in our very first lecture on the black body. Good. What else? The last thing? The very last thing. Regarding this. Suppose that I ask you, what happens if I take a dagger and I apply it to phi n? You might say, phi n I know. Phi n is 1 over square root of n factorial times a dagger to the power n applied to phi 0, right? So if I apply a dagger, well, it's phi n plus 1. Almost, right? It is equal to the following thing. A dagger to the n plus 1, phi 0, but the square root here is not the 1 appropriate to n plus 1. So it's just square root of n factorial. So I might ask, but please, write for me something in which n plus 1 appears. And then you say, okay, let's do it. I put here n plus 1 and here another n plus 1. Okay? Just nothing. But at this point, this is the square root of n plus 1 factorial. Okay? So this is that. So here's the answer. Okay? Applying a dagger to phi n is just equal to phi n plus 1 apart from a square root of n plus 1. This is often encountered, especially when you do calculation of matrix element for perturbation theory. Because after all, if I ask you, okay, what is the matrix element of this with, say, phi n plus 3, okay? And you can answer is 0, okay? But what is the matrix element with phi n plus 1? The answer is square root of n plus 1, not 1. Okay, so you have to be careful with this square root factor. And the same the same happens when you do the opposite. So I apply now A, the killer, to phi n. You might say, I roughly expect that this is phi n minus 1, okay? Only that the problem is that this is essentially 1 over square root of n factorial a dagger to power n phi 0. And remember that when this is in fact erased, partially erased, when this has to act as a killer to phi 0, it has to go through these n things, okay? So the result is that in fact the correct object is the following: square root of n phi n minus 1. Try to show this, okay? So there is a factor square root of n there. These factors here will be encountered also in the angular momentum. When we do the angular momentum ladder operator, J plus and J minus, we will find similar factors, but not precisely the same, okay? And there is a difference, and we will comment on this later on when doing the algebraic construction of angular momentum eigenstates, which in some sense has some similarities, but there is a profound difference. Somehow here you can go up to infinity. There is no upper limit. In the angular momentum, if you go up, boom, you again hit 0. Okay, you are bound to having only a finite number of states. So in some sense it's simpler. Okay, although for other respects it's not simple. Okay, I think we are essentially done with one very last thing about notation. Notation can be a bit confusing. Later on, for instance, we will, for next lecture in fact, we will convincingly adopt the cat notation. So rather than writing things like this, we would certainly write things like phi n, okay? And by the way, this object is interpreted as being x, so the scalar product of x as position eigenstates with phi n. So later on we will use this more than this. So be ready for the cat notation. But even more, sometimes in the book you find this, okay? So this means the n excited states of an harmonic oscillator, okay? Pretty much as this, the eigenfunction associated to energy n plus 1/2. And what about phi 0? Phi 0 also has a certain, first of all, you can always write it like this. But even more, I can write it as 0. 0 means the vacuum. Now, the vacuum of excitations, okay? Remember, this sorry, this vacuum is not really vacuum in the sense that it has a nice wave function associated to it. It's the Gaussian, okay? But somehow there are no excitations. It's the ground state. So vacuum here is a synonym of ground state of my problem. Okay? But if I have somehow in mind photons, then it's the state of the electromagnetic field without extra photons, which doesn't mean that there is no electric field and no magnetic field, but somehow they have the minimum value somehow, okay? So I can create more photons and have larger electric fields, but the ground state of the electromagnetic radiation is the state without photons. Okay? It's not vacuum in some sense because there are fields, but they are the vacuum fluctuations field. Okay, so this is a terminology that sometimes you will find. That especially do not think that this object here is zero, the zero wave function. Zero is not an eigenfunction, in fact. It's a state in the Hilbert space that somehow you just multiply any state by the complex constant zero, you get the zero. But that's not a good state of any system, right? Because there is no probability of finding anything. So it's a very special state which has to be there in every Hilbert space, but somehow it's not particularly full of physical content. While this zero here is the vacuum of fluctuations. Okay? And again, terminology A applied to the vacuum gives me zero. Again, notice the different kind of zeros. This is the vacuum. A is the destruction operator, gives me zero, while A dagger is the creation operator, which accumulates excitations. Okay? That's it. I think we can stop here.